Hi, everybody. Just going to give it a couple seconds to let everybody filter in, and then we'll get started for today. Alrighty, I see that number ticking up, so we'll get started. Good afternoon, everyone, and thank you for joining us today for the live webinar, Feasibility and Performance Analysis for On-Grid Power Projects with RETScreen Expert. I'm Alex Retsky, Digital Coordinator for Annex Business Media and Energy Manager Canada, as well as your moderator for this session. Before we get started here, I just want to extend a big thank you to our sponsor, RETScreen, for putting on this webinar. Before I pass it over to our speaker this morning, I'd like to take a moment to go over a few housekeeping items. Firstly, this webinar is being recorded, so if for any reason you have to leave early or you miss part of the presentation, a link to the recording will be emailed to all registrants in 24 hours. Secondly, the audience is in listen-only mode, so cameras and microphones will be turned off for you. However, questions can and should be submitted to the Q&A folder at the bottom right of your screen, and all questions will be saved for the end of today's presentation. Now I'd like to introduce our speaker for today. Michael Ross. Mike Ross has been a consultant, researcher, and teacher in the fields of renewable energy and energy efficiency for more than 25 years. His clients include governments, companies, public utilities, engineering consultancies, universities, and international development banks and aid organizations. I'd like to pass it over to Michael for his presentation today. Thanks, Michael. The floor is yours.
Thanks very much, Alex. So welcome to all of you for this presentation, this webinar on pre-feasibility and performance analysis of solar and wind projects, on-grid solar and wind projects with RETScreen Expert. There's four parts of this presentation today. The first is going to be a very brief introduction to RETScreen and pre-feasibility analysis. The second part is going to be actually doing a pre-feasibility analysis for a project. That is looking at a 250 megawatt proposed wind farm in Alberta, a hypothetical wind farm, and seeing whether it makes sense to do that project. The third part of this, we'll see how we can do that pre-feasibility analysis even faster than I do it in the second part. And that's using a piece of functionality in RETScreen called the Virtual Energy Analyzer that populates your analysis with some default values. And we're going to apply that for a solar project in New Brunswick. And then finally, in the fourth part of this, we're going to do something completely different. We're no longer going to be looking at projects that are being proposed. We're going to be looking at a project that's actually been built. And we're collecting data about its operations on an ongoing basis. And we want to look at that data and use it for fault detection in the project. So that's for a 6 kilowatt solar project in Ontario. So quickly, what is RETScreen Expert? It's the latest version of a clean energy decision support software available from Natural Resources Canada. It's widely used across the world. It runs under Windows, and it's a free download from www.retscreen.net, but you need a subscription for full functionality, for instance, to save your work. What does RETScreen do? Well, it has 5 main areas of functionality or capability. The first of these is benchmarking. This is particularly useful for buildings and built facilities like that, where you may want to have a very first estimate or rough guess of how much energy your facility either consumes or produces or saves. And you could get that by comparing it to other facilities through a benchmark. And RETScreen contains a repository of benchmarks. The second capability is feasibility analysis. So this is answering the question, is a proposed project technically and financially viable? The third of these capabilities is performance analysis. Now we're talking about a project that's already been built, and we've got ongoing performance data, and we want to analyze that to determine whether the project is meeting expectations and possibly to detect faults in the operation. The fourth of these is portfolio analysis. To this point, I've been talking about individual projects. In portfolio analysis, you group projects together and you look at them in the aggregate. So this allows comparisons across groupings of projects. And fifth, RETScreen is an excellent repository of data and help. So there are online databases in RETScreen that provide climate data, product data, tariff data, things like that. So it can be an excellent source of information. The help can help you learn about the different technologies and how they can be analyzed. And it's also an excellent platform for communicating project details. So a single RETScreen analysis can encapsulate many different facets of a project in a fairly compact, easy to understand form that then you can share with people and communicate the key aspects of your project. In today's presentation, we're only going to focus on two of those functionalities, feasibility and performance. So when we talk about feasibility analysis, what do we mean? Someone has proposed a clean energy project, and you want to answer the question, is this a good idea to do this project? So what do we mean by, is it a good idea? Well, you're going to want to look at how much energy the project is going to either produce in the case of a solar or wind project, for example, or save. Is the project going to be profitable? And when we talk about profitability or financial analysis, we have to be clear on what we're comparing the project to. So is our project going to be profitable compared to some other stated base case? How quickly will you get your investment back? And that's distinct from profitability. Profitability is whether the project makes you richer in the long run. Quickness of return is how quickly the project returns to your pocket the money you've invested in it. Will you be able to get financing from a lending institution for your project? And finally, increasing importance for many organizations in Canada is the impacts on greenhouse gases. So these are all aspects of feasibility analysis. Now, there's an inherent trade-off in feasibility studies of accuracy versus cost. Higher accuracy often implies higher costs. So if you want a more accurate feasibility study, you're typically going to be using tools that are more sophisticated, and that may be more expensive, either in the terms of the time it takes you to use them or the purchase of the tools. Also, you may find that the limiting factor on the accuracy of your analysis is the input data. In order to get more accurate input data, it can be very expensive. For instance, for a wind farm, you may have to install equipment on site, collect monitored data, analyze that over a period of years, and that's all really expensive. So pre-feasibility, as opposed to feasibility, is a quick check to determine whether a project is promising before spending a lot of money on the feasibility study, paying for those more advanced tools, and purchasing or getting more accurate input data. RETScreen deals with a lot of different technologies in feasibility studies, some of them with a slightly more detailed energy model and some with a simplified energy model. The different technologies are shown on this slide. We're going to focus on two of them, photovoltaics and wind on grid. I'm also going to be talking about today the virtual energy analyzer and archetypes. So this is a feature in RETScreen. You can start a feasibility study or a feasibility analysis in RETScreen in a number of different ways. For instance, you can start with a blank project with no default values in your project. And that's how I'm going to start the first study today. You can also base your analysis on an existing analysis. So that could be a project you've already done and you've saved. So you just load it and change values. Or it could be an example or a case study that's built into RETScreen. The third way is based on an archetype. So that's an analysis configured by RETScreen with default values that are tailored to your type of project. And that's done by this so-called virtual energy analyzer. And we're going to show that today as well. So the virtual energy analyzer may permit you to complete your analysis more quickly where its default values are suitable for your project. So that can be of interest. So let's go on to the second part of this, which is actually doing pre-feasibility analysis. So we're going to do this for a 250 megawatt wind farm in Alberta. This is a hypothetical project. It's not based on any real project. It's simply to show how we can do this type of analysis. The location is southeast of Medicine Hat. And the questions we want to answer here are, we want to quickly ascertain whether there's a potential for a profitable project. And then, assuming that it looks somewhat promising, we want to refine our analysis to see if we can make it more accurate. And we want to determine what areas we should focus on in order to do that. So with that, I'm going to turn to the RETScreen software. So the RETScreen software, as you can see, is running under Windows. Across the top here, we have a series of tabs. Not all of these tabs are useful or necessary for feasibility studies. And you'll see some of them disappear when I open a blank feasibility study here. So I'm going to click on feasibility here, and you'll see that some of these tabs disappear. Those are tabs that aren't necessary for feasibility studies. So this is the subset of tabs that we need for feasibility studies. I am now in the location tab, and this is where I can specify the location of my project and where I'm getting climate data from. So I'm going to search here for Medicine Hat, Alberta. And when I double click on that, it brings up this map with Medicine Hat on it. And if I zoom out a bit, I can see that, this tab here, or this thumbtack here, indicates the location of our project, and the other thumbtack indicates the location from which we're getting climate data. So southeast of Medicine Hat is somewhere down here. I can see that this distance is indicated here. We're about 50 kilometers away from Medicine Hat. And we're getting climate data from this location, and we're proposing to put our project somewhere down here. So once I'm satisfied with that, I can click on paste data here, and this will update the data on this location tab. And you can see I have that climate data location information here. So this is where we're located. And this is climate data for that location. So we have monthly and annual average values for a range of climate parameters that are often useful in renewable energy projects or buildings. So for instance, this being a wind project, we're interested in the air temperature and the atmospheric pressure, right? Both of those affect the density of the air, which will affect the wind turbine performance. And we're also interested in the wind speed here. However, you will note that this wind speed measurement here is at a height of 10 meters above the ground. And if we're talking about doing a 250 megawatt wind farm, we will be talking about putting in big turbines that it might be with a hub height of 100 meters off the ground. So a measurement at 10 meters isn't terribly useful, and it's not going to be very accurate, even if we try and adjust it to account for the difference in wind speeds at 10 meters and 100 meters off the ground. So this wind speed here is not going to be very useful for us. It's not adequate for our purposes. It's also not adequate because, as we mentioned earlier, we're about 50 kilometers away from our project location in terms of our climate data. And the wind resource varies as a function of location over very short distances due to changes in terrain and roughness and things like that. So for those two reasons, this height and the distance between our climate data location and our project, this wind speed is not going to be sufficient for us. However, the air temperature and the atmospheric pressure, those don't vary over short distances. So those are going to be useful information that we can use in our analysis. The next thing I'm going to do is go to the facility page where I can configure the project or configure the analysis to do the type of analysis I want. So the first thing I want to verify is I've got feasibility selected here. That's correct. For the facility type, I have power plant selected. That's correct as well. However, by default, it's selected photovoltaic is the type, and I want to change that to a wind farm. So wind turbine is select here. And I could enter other data here, but a lot of these are gray cells, and gray cells in RETScreen are just for informational purposes. So they're not going to affect the calculations that RETScreen is doing. So in the interest of moving on to more interesting things, I'm just going to ignore them and go on to the energy page here. So on the energy page, when I get there, you'll see that there's this ribbon menu here, which has step 1, step 2, and step 3. So that gives me some guidance about how to proceed here. I should basically follow that order. And you'll also see that these items that appear in the ribbon menu are echoed in this left-hand navigation pane here. So I can navigate around my analysis, opening different windows or different pages here by selecting items from this left-hand navigation pane. And if I want to add an item to this left-hand navigation pane, I can click on an item up here that has that plus sign indicating add. So for instance, at a certain point in time, I'll want to add power generation technology here. But the first step is to look at electricity and fuels. That's step 1. And I see the top part here, there's a fuel being indicated. And that can cause confusion because people can say, this is a wind farm. Why do I have to talk about natural gas? Well, a fuel is included by default in RETScreen, but it doesn't mean we have to use it in our analysis. So this is equivalent to the situation where we're building a wind farm and there's a gas distribution line running beside the wind farm. Well, the gas is there, but we don't have to use it. Well, in RETScreen, we got natural gas here, but we're not going to use it for anything. So we can just ignore this. On the other hand, we are going to want to sell the output from this wind farm. So we have to specify what the average price we're going to sell it for is. And I'm going to put in here a value that I'm picking out of thin air because this is a hypothetical project. And I'm going to put in 5 cents a kilowatt hour here. So that's the average rate at which we sell the power output from this turbine. And then I've dealt with step 1. I go to step 2 here and I add a power project. And the one I want to add is a wind turbine project. So this is going to be my 250 megawatt wind farm. You'll see that there's level 1, level 2, and level 3. In RETScreen, these buttons are used to indicate what level of detail we want to do this part of the analysis in. And level 1 is the most simplified, and level 2 and 3 are more detailed. So for example, here in level 1, I would have a very simple analysis where if, for example, I was very familiar with wind projects in Alberta, I might be able to skip over the details of my analysis and simply say, this is a 250 megawatt project with a capacity factor of, say, 50%. Now, for those of you who are not familiar with capacity factor, that's a term that refers to the average output of a power project expressed as a percentage of its nameplate or nominal capacity. So by saying 50% here, I'm indicating the average output from my wind farm would be 125 megawatts. So this would be a way to quickly specify our project with the minimum amount of detail. It gives us the annual electricity being exported to the grid is 1 million megawatt hours per year. And the annual electricity export revenue is about $55 million per year, assuming that we're getting paid 5 cents a kilowatt hour, what we just specified moments ago. So this is very useful if you're that expert who already knows that the capacity factor for a project such as this is about 50%. However, for the rest of us, we would want RETScreen to tell us what the capacity factor is based on the wind resource and based on the equipment we select. And in order to do that, we can go to level 2, right? So level 2, we have more detail in our analysis here. And here's some cells we're going to have to fill out to specify our wind resource. Some cells we're going to have to fill out to specify our equipment. Here is some further cells that talk about loss factors associated with our equipment. And then finally, at the end, we have as an output here, the capacity factor. So it's going to calculate that for us based on what we provide in these other cells. So let's return to that and fill this out. Now, the first thing we have to specify is either the wind speed or the wind power density. And I'm going to specify the wind speed, but you'll recall that I said that using this 4.2 meters per second at a measurement height of 10 meters above the ground is going to be completely inadequate for this analysis because it's 50 kilometers away and our turbines that are about 100 meters off the ground hub height, not 10 meters. So we're going to need a high resolution source of wind speed at a hub height of about 100 meters off the ground. And we can get that by clicking on this button here. So when I click on that, it opens a website outside of RETScreen. It's actually a website operated by the World Bank. And this is a worldwide wind atlas providing terrestrial wind speeds at different heights. So I'm going to search for Medicine Hat. And clicking on that, it takes me to Medicine Hat. I'm going to zoom out here so I can see the general area here. And you can see that indeed southeast of Medicine Hat, there are some areas that are quite windy. So I'm going to pick one of those areas. And of course, in the real world, you can't be very casual about picking these areas. You have to see what the land use is. So for instance, there is a park in this area, and you're not going to typically be putting wind turbines in parks. You'd have to look at your proximity to transmission facilities for transmitting power. You might look at whether there's cottages in the area, whether there's migrating bird or bat populations in the area, or they're going to be coming through. So those are all real world considerations that I'm ignoring. I'm just going to use this to estimate the mean wind speed, which I've selected here, at a height of 100 meters, which is indicated down here. And in order to do this, I'm going to pick this draw polygon tool here, and I am going to pick an area here, which I think we might be able to, build a wind farm in. And when I click on that, it indicates I've got about a 330 square kilometer area here. So it's a really big area. But over here on the right-hand side, it indicates the wind speed at a height of 100 meters off the ground for the 10% windiest areas within this area. So we'd have some flexibility to place our turbines here. Obviously, we're going to place them in the locations which are the windiest. And so these we can estimate as being these 10% windiest areas, which have an average wind speed of about 9.55 meters per second. So I'm going to use that in RETScreen. I'm now going back to RETScreen, and I've now got this estimate here of 9.55 meters per second. Now that's not at 10 meters measurement height, that's at 100 meters height. So I put that in, and now I've got a much more reasonable starting point for my estimates of the wind speed. However, there's no guarantee our turbines will be exactly at 100 meters. They might be, say, at 90 meter hub height or 110, something like that. So we're in the ballpark, but we may need to do a little bit of adjustment to make up for any differences in height between our measurement height here and the actual hub height of the turbine. And we can do that using a profile that approximates how wind speeds change with height off the ground. And to calibrate that profile, we use something called the wind shear exponent. And you can read about that by hovering over this parameter, wind shear exponent. That causes this little question mark to appear. And then I click on that and I get help. You'll see that help explains what this is, and it gives us a typical range of values. And it also says a value of 0.14 is a good first approximation when the site characteristics are yet to be determined. So that's a good indication that help in RETScreen is actually quite helpful. And you'll find that often if you're trying to figure out what a parameter is or what to enter, it's good to consult help because it tells you what it is, what the potential range of values is, and it often gives a suggestion for how to proceed. So I'm going to assume that our site characteristics aren't yet determined, and I'm going to use 0.14 here. And I'm not too fussed about what the exact value should be because I'm starting out in the right, I'm in the vicinity of the correct height by starting out with a measurement of 100 meters. So not a big adjustment is going to be required. Now I need the air temperature and the atmospheric pressure. Those do not change over short distances like the wind resource does. So I can use the values from Medicine Hat here. So I'm going to put in 5.5 degrees as the average annual temperature and 93 kilopascals as the atmospheric pressure. And those are used by RETScreen to estimate the density of the air, which of course affects the mass flowing through the rotor and therefore the amount of energy it produces over the course of the year. Now I have to specify the wind turbine. And the key thing there is to provide a power curve. That is, how much power the turbine generates as a function of the instantaneous wind speed. And there is a database built into RETScreen to help me do that here. So I am going to click on See Product Database here. And I can see that there are, a range of manufacturers here. And I'm going to look at Vestas turbines here. There's a particular turbine I'm interested in looking at based on this wind resource. It's the Vestas V90 1.8 megawatt with a 105-meter tower. So the V90 indicates that it's a 90-meter rotor, and the 1.8 megawatt refers to the AC capacity of the generator on the turbine, and the 105 meters is the hub height. So I'm going to click on that, and there's the power curve for that turbine, that particular turbine. So to interpret the power curve, right, like for a value of 8 meters per second, if I had an anemometer and I measured the wind speed at a given point in time, and it said, right now, your wind speed is 8 meters per second, and then simultaneously I looked at the power output of the turbine, I should be seeing a number around 863 kilowatts. And similarly for the other numbers on here. So I have a power curve here. That's for a single 1.8 megawatt turbine. You might recall our project we're aiming to have a 250 megawatt project. So I'm going to need a few of these turbines. If I do quick mental math, it's about 139 of them. That works out to a capacity of 250 megawatts. So if I'm satisfied with that, then I can click on Paste Data down here, and that power curve and these other numbers get pasted into there. Now, one thing that is interesting is you'll see that one of these numbers is the hub height, and beside it is the wind speed at that hub height. And we can confirm that at 105 meters, the wind speed is slightly different, 9.62 meters per second, compared with what we specified at 100 meters. So it's used this wind shear exponent to adjust the wind speed based on the hub height here. If we look down here, we see there's our power curve, and we see an image of that. It's the green line here. So at low wind speeds, you don't get any power out. Then it ramps up starting at about 3 meters per second. And then it reaches a maximum around 12 meters per second, and it holds that out to about 25 meters per second. Now, that's the power curve for a turbine that is functioning under ideal conditions. The real world is never ideal, so we're going to have to specify in what ways we can expect the performance to be deteriorated compared with those ideal conditions. One of them is the array losses here. So array losses refer to the decreased wind resource available to downstream turbines due to upstream turbines having a wake. And we click on Help to get some guidance on what we should specify here. And we see that array losses for a single turbine installation are 0. That makes sense. A turbine isn't wind shaded by upstream turbines if it's the only turbine around. But well-designed clusters of less than 8 to 10 turbines here should keep array losses below 5%. So I'm just going to use that as a first guess, 5% here. I could similarly look at the help for these other things, but I'm just going to use some values that I think are reasonable here. So airfoil losses, that's due to, say, insects or ice or snow, reducing the aerodynamic properties or changing the aerodynamic properties and the efficiency of the turbine blades. Miscellaneous losses due to things like off yaw operation, I'm going to say are 2%. And then availability, which is the fraction of the time that the turbine is available to generate power should there be sufficient wind. So 97% of the time, we're going to assume that the turbine is in a state where if there's wind, it can generate power. Doesn't mean it's operating 97% of the time, because the wind doesn't blow necessarily 97% of the time. It's just saying that if there was wind, it would be available to do it. And we see that based on what we've entered there, our capacity factor, as calculated by RETScreen, is 48.7%. So what, 120 megawatts on average, something like that. And using that, it has been able to calculate the annual output of 1 million megawatt hours per year and about 54 million dollars per year in revenues. We have here some cells for entering the initial costs and the O&M costs. So for the initial costs, I'm going to click on this cost database over here, and it's going to open this database, which shows typical installed costs in dollars per kilowatt of capacity as a function of the size of the project, right? There's economies of scale for these types of projects. Bigger projects cost less per kilowatt than smaller projects. And that's reflected here. For wind turbine, a good starting guess would be around 2,000 Canadian dollars per kilowatt. Now, this is just a starting guess. We're going to revisit this later on. But for now, I'm going to use that as my estimate of the cost of this project. So it's a $500 million project. And for the O&M costs, I'm going to do a similar thing here. I'm going to open this cost database, and it gives me an estimate of the O&M costs in dollars per kilowatt of installed capacity per year. So $36 per kilowatt per year. And that indicates that I'm going to spend about $9 million in an average year servicing these turbines, keeping them operating in one way or the other. So that completes this energy tab here. My next thing is to go to the cost tab here. And when I look at the cost tab, I see that my costs have been carried over from the previous page. So everything is fine there. I don't need to add anything here. If I wanted to, I could indicate how these lumped costs are broken down into different line items. And I could do that with, quite a bit of detail by going to a level 2 analysis here. I could also include some periodic costs there, but for this demonstration, I'm satisfied with that. And therefore, I'll go on to the emissions tab here. And this is where the GHG emissions reductions for the project are calculated. And in a level 1 analysis, like we're looking at right here, we see that RETScreen has a database where it has the emissions associated with a megawatt hour of generation from the existing grid sources. And it tells us that for Alberta, about 0.59 tons of CO2 are emitted per megawatt hour generated for grid in Alberta. And assuming that our wind turbines don't generate that level of emissions, we can see that the emissions reductions compared with getting the electricity from the grid are about 630,000 tons of CO2 per year. So a significant reduction there. Now I will go to, and we're going to revisit this. So we'll be back, but for now, we're just going to go onto the finance page. And here we kind of bring together what we saw on the energy cost and potentially emissions page to assess the profitability and quickness of return of this project. Now, I first want to make sure that my financial parameters are reasonable. I'm okay with an inflation rate of 2%. That's indicating that both my electricity costs, or my electricity price for electricity, and my O&M costs are inflating at 2% per year over the lifetime of the project. Lifetime of 20 years, that's appropriate for a wind farm. The debt ratio of 70%, well, I'll leave that as is right now. And then debt interest rate of 7% and debt term of 15 years. So we're putting in, our investors are putting in 30% of the initial cost of the project. Lending institutions are providing the remaining 70%, and they're charging 7% interest rate, and we need to pay it back over 15 years. And based on that, we have a project that isn't awful, but it's got a pre-tax IRR and equity of only 10%. So typically you wouldn't have investors leaping over that. So one thing we might think about is whether we've missed any revenue streams. And I would argue that we have, right? Going back to the emissions page, we got 630 tons of GHG emissions reductions per year. Presumably someone's going to pay us for that. So let's put a price on that. Let's assume that the GHG reduction credit rate is $65 per ton. And let's assume that over the 20 years of the project, we can get paid this amount. And we know that this is going up over time. I'm going to assume that it's going to double twice over the 20-year lifetime of the project. So that works out to roughly 7% escalation rate. At the end of 20 years, that would work out to about $260 per ton. Is that reasonable? I'm not sure, but let's just assume that's a reasonable assumption here. The GHG credits transaction fee would be anything that we have to pay in order to monetize these GHG reductions. So presumably there's going to have to be some auditing done to ensure that we're actually achieving this, and that's going to cost us something. So I'm going to assume that 10% of our GHG emissions reductions credits are going to be, essentially the value is going to be transferred to this organization. But that still leaves us with about 37 million $37 million of revenues per year from GHG emissions reductions. So that's pretty significant. And that indeed shows up here on the finance page. Including that, we have a pre-tax IRR on equity of 38%, which is really extraordinary, right? So that seems almost too good to be true. And that makes me think, well, maybe we should go back and check our assumptions. And in order to determine which are the key parameters that I should really focus on, I'm going to go to the risk analysis here. And I'm going to ignore the sensitivity at the top here. And I'm going to focus on one part of this, which is the impact graph when I'm looking at the pre-tax IRR and equity. This chart here shows me which are the variables that have the biggest impact on the pre-tax IRR and equity. So I see right now the biggest one is the debt ratio, then the initial costs, then there's some other things that are somewhat important, and then things like the debt interest rate and the O&M costs, they're really not that important at all. So I'm actually not going to focus too much on those right now. I'm going to start with these biggest, most important factors here. So the first of these, the debt ratio. Let's go back to the finance page here and let's contemplate this 70% debt ratio. Does that make sense? So maybe I go to Alberta and I talk to people, and what they might tell me is that, listen, unless you have a government offering you a 20-year contract to purchase your electricity at a fixed price, you're going to be selling into the Alberta market. So you might be dealing with shorter term contracts or even selling onto the spot market. And therefore, it's going to be hard for you to guarantee you're going to get paid 5 cents a kilowatt hour over the lifetime of the project. Therefore, it's a much riskier project, and lending institutions may not be so enthusiastic about putting up 70% of the cost of your project. In fact, you might find that 30 to 40% is all they're willing to loan you because they want you as the investor to have significant skin in the game to make sure that this risk is reasonable. So when I do that, I put 40% as the debt ratio here. I see that that does indeed have a big impact on my pre-tax IRR and equity. You saw this graph change when I changed that. We're down to 26.2. So still a very good project, but much less good than it was when I had perhaps an overly optimistic debt ratio here. The next thing, I want to go back to the risk analysis here, see what else we got. Now, the big thing is initial costs. So let's go back to the initial costs. And if I go to the energy page where these initial costs are specified, I see that we're looking at $2,000 per kilowatt here. Once again, I go to Alberta, I talk to people. Maybe I find that that's a little high or a little low. When I've been looking at advertised costs for recent projects in Alberta, I've seen lower numbers than that. So I'm going to put in $1,600. I'm not an insider in the Alberta wind farm business, so I don't know if that's appropriate or not, but at least some people are talking about doing projects at that initial cost. So now our $500 million project is a $400 million project. And obviously that has a big impact on the financial analysis. We're back up to over 30% internal rate of return. The next thing, let's see what else we've got here on the risk page. Well, the electricity being exported to the grid. is the next thing here. So let's go back to the energy page. Well, we can look over all these assumptions we've made and determine whether they're reasonable or not. So one thing I might want to do, for example, is I might want to change my turbine. So I picked a 1.8 megawatt Vestas turbine. But if you look at recent projects in Alberta, they're using more recent turbines than that. So 4 to 5 megawatt turbines, and they're going to have a slightly different power curve. So I might want to go and find the power curve for the turbine that I'm actually thinking about using and enter that into RETScreen here. And it's actually not a lot of work, right? I can just overwrite these values. And there's only about 10 values I have to overwrite because at low numbers, low wind speeds, the value is 0. At high wind speeds, it's flat at the rated output of the turbine. So I only have to enter in about 10 numbers here. I chose this older 1.8 megawatt turbine because the power curve, because it's appropriate for the wind resource we have there, and it's available as a power curve in RETScreen's database, and some more recent turbines aren't necessarily there yet. So that would be one thing I could do. I could update that. I could also put in some measurement equipment at the site to get a better estimate of my wind speed. I could do a level 3 analysis where I would have, monthly wind speeds. Those are things I could do to improve this. The other thing is eventually I might have, so much expertise applied to this problem of estimating the wind resource and the power output of my turbine that I'd be using really sophisticated engineering design tools to come up with an estimate of the capacity factor. And once I've done that, I don't need to throw away my RETScreen analysis. I can incorporate the output from those other tools into RETScreen, perhaps by going back to a level 1 analysis and saying, okay, I'm not going to use RETScreen to estimate this anymore. I've got these other, very advanced computational fluid dynamics tools to estimate this. I am going to take their output, say they tell me the capacity factor is 47.5%. I'm just making that number up. I take that out of their output, drop it into RETScreen, and now I can continue to use the rest of the functionality in RETScreen. So now I have perhaps improved my accuracy in terms of electricity being exported to the grid. If I go back to the risk page here, oops, that's interesting. This is a bit of a surprise. I've obviously done something wrong. Oh, yes. I forgot to put in the costs here. So we had, I think, $1,600 here per kilowatt, and here it was $36 per kilowatt per year. And when I go back to there, I go back to the risk page, and I can look at what are the next most important factors to consider here. So I've dealt with the initial costs. I've dealt with the electricity export to the grid. The next thing here is the export rate. So if I go back to the energy page, you might recall I am assuming that I can get 5 cents per kilowatt hour for this. Once again, if I go to Alberta and talk to people, they may tell me that's overly optimistic. Wind projects may be getting less than that. So if I lower this to say 3 cents a kilowatt hour, how does my project look? Obviously, it's going to have a big hit, but we still actually have a profitable project. And that reflects the importance of the GHG emissions reductions. They're really carrying this project at this point in time, right? And then we go back to the risk page here, and we've worked our way down to now what's really of key importance is the GHG reduction credit rate. So let's go back to the emissions page here and see if we trust all our assumptions here. Well, the first thing we might want to do is see is this a reasonable estimate of the emissions reductions? And one thing we might do is look that up, and we might find that there's actually a document, that's published quite frequently by the government of Alberta called the Alberta Carbon Offset Emissions Factors Handbook. And it actually stipulates what the correct value to use, according to the government of Alberta, for this emissions factor per megawatt hour of grid electricity being generated. So if we're displacing electricity from the grid using renewable generation, so wind turbines, these are the emissions factors we should be using according to the government of Alberta. And we can see that there's two issues here. First, these are lower than the number we're using. And second, they're declining over time. So somehow we're going to have to approximate this in RETScreen. So my goal here is going to be to pick a number around, say, 0.43 to approximate the situation for the first 5 years of the project, and then 0.34 for year 6 and beyond. So that's what I'm going to try and do here. And I can't get the exact decline in there, but I can approximate that situation in RETScreen. So how do I do that? Well, one approach would be to say, well, we want an emissions factor of 0.43 here. But the problem is that only works for the first 5 years of the project, right? We can't put in the 0.34 for year 6 and beyond. So what do we do? Well, we can go to level 2 here. And a level 2, first thing we're going to do is we're going to copy the information we had in level 1 over to level 2 here. And that means that at the bottom here, we have our same pricing for GHG emissions reductions as we had before. But here we have a mix of sources on the grid that we can use to estimate the emissions factor. So right now it's 100% natural gas, but if I do a little trick here and I say it's 90% natural gas and the rest of that is, say, wind power, I can see that I end up with the GHG emissions factor that's about 0.43. So the situation I want to model for the first 5 years of the project. And then there's this little box here that says baseline changes during the project life. I click on that and I can say, in year 6, reduce the emissions factor by, say, 20%. And that takes us down to 0.34, which is what we wanted. So now I have a situation where I have a more accurate estimate of the emissions reductions that I'm going to be able to justify for this project based on that guidance from the government of Alberta. So we see from years 1 to 5, we're getting 411,000 GHG tons of CO2 equivalent per year. Year 6 and beyond, 329,000. And going back to the finance page, we see that, our project took a hit, but it still is somewhat promising here. So to summarize this, what I would conclude is that this project has some promise. And we know what are the factors we need to focus on to make this more accurate, this analysis more accurate. But it appears that there's enough promise in this project that it might be worthwhile investing more to come up with a more accurate feasibility study. And we've been able to do that relatively fast. Now, the third part of this presentation is about doing that even faster by using this virtual energy analyzer to quickly do an analysis of a solar project in New Brunswick. So this is a 10 megawatt project located near Fredericton. And we have a specific question we want to answer. That is, our investors have told us they want to achieve a 12% internal rate of return, or return on equity. What is the lowest price that we can sell the output from this photovoltaic system and still achieve that 12% internal rate of return on equity? And while I'm demonstrating this, I want you to reflect on how quickly we can do this analysis by using the virtual energy analyzer. And I also want you to reflect on how similar the analysis is to the wind feasibility study. You'll note that really all the differences are contained in the energy page, which is obviously different than for solar and wind, but everything else looks pretty much the same. So I'm going to go back to my analysis here, and I'm going to close this one. And I'm going to use this virtual energy analyzer here to launch a new analysis. And this is indeed a power plant, but it's a photovoltaic power plant with a 10 megawatt size. And we want to locate this in Fredericton, New Brunswick. So double clicking on that. I'm just going to accept that as being the location. And I click OK, and I get this RETScreen configuring the software with default values. So now if I look at the different screens, they're actually already filled out. So here's my location. That's fine. The facility page, it's a feasibility study for a photovoltaic power plant with 10 megawatts output. Wonderful. I go to the energy page. The thing we're going to be playing with is the electricity export rate, right? I want to see how small I can make this number and still see on the finance page a 12% internal rate of return on equity or higher, right? Also on this page, I have my 10 megawatt photovoltaic project. So let's check to see whether what RETScreen's entered here is reasonable. I quickly glossed over this, but I specified a fixed project, meaning I'm not using a tracking system for the solar modules. So that's fine. The azimuth is 0, which in RETScreen indicates south facing. I'm happy with that. The slope is 46. So that's the latitude at this site. And that would make sense if we absolutely want to optimize or maximize the collection of energy year round. But it does have its practical downsides. You have to space your rows of photovoltaic modules further apart, because the more vertical the module is, the further it casts a shadow behind it. So you have to space rows further apart. And that means it takes up more land or more roof space. So I'm going to lower this to 30 degrees here, which still should be high enough to reduce any snow accumulation. And when I did that, you'll see that the daily solar radiation on a tilted surface here changed. So it's being calculated by RETScreen based on the climate data here, and then being adjusted according to the factors we specify there. So there I've got my solar resource. Down here, here's my photovoltaic system. It's 10 megawatts. That's fine. That's what I wanted. The efficiency, that seems a bit low to me. I could update that, but really all it's changing is the solar collector area here, right? That's all that changes there. So I think recent panels around 19% seems reasonable. I might assume that my modules are bifacial, meaning they're sensitive to light on both the front side and the rear side. That's of increasing use in North America for larger projects like this. So I might assume that over the course of the year, that boosts my output by 10%. That is, I'm not just collecting light on the front surface of the modules, I'm also collecting light from the rear surface of the modules. So reflections off the ground, off snow, for example. Miscellaneous losses of 15%. I could look at help, but it's actually a reasonably conservative figure. I'm quite happy with that. The inverter efficiency, that seems a bit low to me. If we look at help, for example, here, it says a value of 97% is suggested as a starting point. And I would even go beyond that. For a big project like this, 98% efficient inverter is reasonable. The capacity inverter, we typically size them smaller than the DC capacity of the photovoltaic modules. Why? Because photovoltaic modules are only going to be putting out 10 megawatts of power when you got bright sun and cold temperatures. And that confluence of climatic conditions or meteorological conditions does not occur that frequently. So most of the time you're putting out well less than 10 megawatts. So why purchase a 10 megawatt inverter when you don't need 10 megawatts of capacity the vast majority of the time? And I would argue that even 9,000 is a bit on the high side. I'm going to put in 8,500 kilowatts here. Miscellaneous losses of 1%, probably a bit conservative, but I'm happy with that. Here it's calculated the capacity factor, 14.9%, much lower than for the wind farm. You might even say, well, that looks really low. If you're familiar with solar projects, you might say that looks really low. Keep in mind, in RETScreen, this capacity factor is calculated on the basis of the DC power capacity and not the AC power capacity is often done elsewhere in the industry. So that accounts for some of that difference. And our generation is indicated here at the bottom. We've got about 13,000 megawatt hours per year. So that's $1.3 million in revenues, assuming that we're getting paid 10 cents a kilowatt hour. But of course, we're going to change that number. It's a $13 million project, O&M costs of $140,000 per year using these default values. And I'm going to accept those for now. Next, we can look at the cost page. I think I'm happy with that. I'm not going to change anything here. On the emissions page, I see that we have about 3,000 tons of emissions per year. That's a reasonable amount. I'm not going to put any value on that yet. So let's go on to the finance page here. I see that RETScreen's actually done not just the level 1 analysis that we were looking at before, the simplified analysis done a level 2. So let's just check to see whether the parameters are reasonable. Inflation and fuel cost escalation rate of 2%, I can live with that. The discount rate of 9%, I know is wrong. Why? Because we've been told that our investors are targeting a 12% internal rate of return. So that means that our discount rate is 12%, right? Because if we achieve an IRR of 12%, then we're going to want to see the net present value go precisely to zero. So the discount rate is 12% then. Project life of 20 years is a bit pessimistic for a solar project. I'm going to put in 30 years there. I'm not worried about the debt ratio and the debt interest rate and the debt term. I'll leave those as is. You could argue about whether they're realistic or not, but for the purpose of this demonstration, I'm going to leave these as is. And I see that I have a pre-tax IRR of 13%. So that's higher than the 12% target and discount rate. Therefore, we have a positive net present value. But we've also missed some revenue streams, right? I think if we go back to the emissions page, we could probably get some payment for this. So let's put in a GHG emissions reduction credit of $65 per ton here. And maybe I'll be a bit more conservative here because it's a 30-year project. I'll say 30 years, but with an escalation rate of only 5%. And once again, I'm trying to approximate the real world situation. And I think in a first analysis, this is reasonable. I'll put in a 10% transaction fee there as well as I did in the last. And that means I get revenues of about $176,000 per year from this. And of course, that's going to boost my internal rate of return on equity here quite significantly, 17.2% now. So if I'm getting 17.2%, and I know my investors would tolerate 12%, I in theory could lower the price I'm charging for the output of this solar project and still satisfy my investors. And I might want to do that because I'm going to be in competition with other project proponents and we're going to be competing on price. So if I can sell for less than them, then I might get to do my project and they might not get to do theirs. So going back to the energy page, what I'm going to do is I am going to adjust this value here in order to achieve an internal rate of return of 12%. And so I don't have to jump back and forth between the energy page and the finance page. I'm going to launch this dashboard here, which brings up this floating window over here. And I want to look here at the financial viability parameters. So we see that currently I've got a 17.2% internal rate of return, obviously a positive net present value. Let's just by trial and error adjust this. So if I put in 6 cents a kilowatt hour, I should see that drop. And it dropped too far. I want to achieve 12% here or 0 in the net present value. So I've gone too far. If I go to 0.08 here, I'm a little bit over. So I could actually lower it just a little bit more, say, whoops, at 7.8 cents a kilowatt hour, I'm right at 12%. So that's the floor. That's as low as I can lower this and still satisfy my my investors. And I could compare that with the current electricity tariffs in New Brunswick by clicking on this database here, right? And I could see that currently the retail prices of electricity are 11 to 14 cents a kilowatt hour. So that's good. I mean, we're able to generate electricity at a rate quite a bit below the retail rate. So that suggests that we might be able to actually do something here. So that is this virtual energy analyzer doing a very fast analysis of a solar project, even faster than the wind project we did before. Going back to our presentation, we get to the last part of this, which is performance analysis. And once again, I'll mention that this is a complete change in approach. Up to this point in time, we've been looking at the feasibility of a proposed project. Now we're looking at the performance of a built project. So this is an actual real world project. To this point in time, I've been dealing with hypothetical examples. This is data from a real project. And it's located in Markham, Ontario. It's a very small PV system, a 6 kilowatt PV project with 2-axis tracking. So it always tracks the sun so that the sun's rays arrive perpendicular to the surface of the photovoltaic array. And what we're being provided with is an Excel file with electricity fed onto the grid for each billing period from 2011 to 2018. And we're being asked to look at this data and tell whether the system is performing well, just looking at the Excel data. And I want you to think about whether it's easy to do this or not. And if it's not easy, why is it not easy to do this? So let's look at the Excel data we have to work with. So here is the file we've been handed. So there's the year and the month, and then the billing start date and the billing end date. You see it starts in 2011 and it goes to 2018 here. And then we have 2 columns here, the kilowatt hours of electricity that are fed onto the grid, and then the revenue that the utility paid us essentially for our generation here. And if I scroll down, I see that these kilowatt hours produced per billing period change from month to month or from billing period to billing period. It's really hard to identify whether the system is functioning correctly. I mean, there's one value that stands right out and tells us there's a problem. Between mid-March and mid-April 2017, we got 0 output. Obviously, something went wrong there. But the rest of these numbers, I would argue it's not that easy to tell just by looking at them whether this is reasonable or not. So why is it not easy to detect faults here, other than that one extreme fault? Well, 2 reasons I would posit. One, you look at the billing date. It changes all over the place. So our billing periods are not all, say, 30 days. Some of them are, say, 28 days. Some of them are over 40 days. So when we see variability in the kilowatt hours produced in the revenue, we have to ask, is that due to variability in the functioning of our system, or is it simply that the billing period is shorter or longer than the previous and the next billing period? The other reason why it's hard to assess whether there's faults in here is because we expect there to be variability in the production of a photovoltaic system based on the meteorological conditions. Summertime, we expect this photovoltaic system to produce more than in wintertime because there's more sunshine. So it makes it hard to tell whether the system's functioning correctly or not when there's variability coming from both the length of the billing period and the meteorological conditions. And what we'd like is a tool that removes that variability, leaving behind only variability that's due to the functioning of the system. So then if there's a fault, it shows up, that there's a problem. That's what we would like. So how can we get RETScreen to do this for us? Well, here's my general approach. I'm going to build a single table, and I'm not going to use Excel. I'm going to use RETScreen to do this. I'm going to build a single table with each row in the table being for a single billing period. And for each billing period, I want to have the solar radiation that's striking the surface of the array during that billing period, the average air temperature during the billing period, and the photovoltaic output and revenues for that same billing period. Because I think these 2 things, the solar radiation and the air temperature, are what is mainly going to determine the variability in the photovoltaic output, at least when it's functioning correctly. And therefore, I'm going to want to have those all in the same table. And once I've got those on the same table, then I'm going to use regression, this mathematical technique for fitting an equation to data to find the equation that best estimates or predicts this PV output, kilowatt hours per billing period, as a function of the solar radiation and or the air temperature. And I'm going to call that equation my baseline. That's just the terminology that's used in the field. Now, how is this equation going to help me? Well, it can do 2 things in terms of fault detection. First, for each period, I can subtract the predicted output from the measured output. So I have my measurement and my prediction. I subtract the two. If I see a big negative number, then I know there was a big problem during that period, right? I predicted something and I got way less when I measured it. However, that's not going to detect all problems because I can have more minor problems that fall under the radar. They don't show up as this big difference, but if they persist over time, then over time, their impact can be really significant in terms of lost production. And those won't be detected by looking at a single billing period. So in order to detect those, what I'm going to do is I'm going to take that same difference between the measured, or I'm going to take the measured minus the predicted output, and I'm going to look at it for each period and sum from one period to the next. So over a series of billing periods. And we're going to call this the cumulative sum of differences, or the Q sum. And the key thing here is if there's a difference, a persistent difference between what I predict and what I measure, then from one billing to the period to the next, that persistent bias is going to accumulate. And it's going to get bigger and bigger and bigger. And it's going to become apparent there's a problem because the difference between the two, the sum of the differences between the two is going to get bigger over time. And that's going to tell me that my expectations are not being met. The other way that this is useful is by looking at the slope of the line. So if I graph the Q sum as a function of time, if I see it rising in a straight line or falling in a straight line, I know there's this persistent difference, but the difference is the same in each billing period. That's why it's a straight line. If I see the slope of that line change, though, that tells me that something in my system has changed because my equation isn't changing. My predictions are all going to be the same, but all of a sudden the persistence difference between what I'm measuring and what I'm predicting has changed. So that tells me there's a problem. So we're going to do this analysis quickly, and we want to answer these questions. Have there been problems? Are there ongoing problems? And when did problems occur? We also, assuming we have time, we're going to look at how much this project should generate in a typical year. And that might be useful if we wanted to compare it to, say, the output of a simulation that we did prior to building the project to see if we're matching expectations that way. And we want to see how actual generation has compared with what it should have generated if the system was always functioning correctly. So this is what we want to answer with this performance analysis. So let's go back to RETScreen, and we are going to start, we're going to start a new analysis. So I'll close this one, and we're going to start a performance analysis here. And the first thing we're going to do is we're going to specify our climate data location. And I told you that this project is in Markham, Ontario. And in the real world, I'd want to situate that very precisely where the project actually is. But for this, I can just accept that it's in that general area. And now I will go to the facility page here, and I'll ensure that we have this all configured correctly. It is a photovoltaic power plant. It's a 6 kilowatt one, so I'll enter that. Now I get to a tab that you will have not seen before, in this presentation at least, which is the data tab. And our goal here is to build a single table, as I mentioned, which has both the photovoltaic generation and revenues, and for the same billing period, for each billing period, the solar radiation on a tilted surface and the air temperature. So that's the goal in this tab. And I'll start by getting the data that I just showed you in that Excel file, the electricity production data. So I'm going to get this out of this Microsoft Excel file. When I go to import that, it asks me which file this is. So I go, okay, that's that file. It correctly detects that the first line is a header. That's fine. And then if I go on here, it tries to interpret each of the columns in the file. And I don't actually care about the year and the month here. So I'm just going to tell RETScreen not to import these first two columns because they're not what's important to me. What is important is that I have the beginning date and the ending date for the billing period. So it's got the beginning date it hasn't correctly interpreted the end date. So I click here and say end, and then it's got that correctly interpreted. It's figured out that this next column is the kilowatt hours of electricity production, and the final column is the revenue. So that all looks good to me. I click calculate here, and it fills out this table. And you'll note that it's actually added a column, which is the duration in days. And we see that indeed, these are varying from, say, 28 days to 45 days. So there's a lot of variability in the length of the billing period. Now, that's great. I need weather data though now. And one reflex might be to say, great, I'll go back to the location page and we have data here, right? We have the solar radiation. It's on the horizontal, but maybe we can deal with that somehow. And we have the air temperature. Wonderful. This is not weather data. This is climate data. This isn't changing from year to year. This is the typical for, or these are the numbers for a typical year. And what's driving the variability that we see here is weather in each of these months. So we're going to need a different source of data. And fortunately, RETScreen has that. If we click here to add a new table, we're going to add a weather table. And RETScreen has an arrangement with NASA where you can get, for any location on the planet, weather data on a daily basis or even a sub-daily basis. So you click OK here, and then you specify the dates. And I'm going to go back way back, say to 2000. So I get a long series of data, and I click OK. And I expect this is actually not going to work for me because I've been having problems connecting the NASA data website. It's just me though. Other people are doing fine. So I've got a problem here. So what I'm going to do is I've got a backup plan, right? I am going to delete this, and I am going to load the same data, but in a file I happen to have saved the last time I did this demonstration. So I'm going to load this from Microsoft Excel file. And this way you get to see the other way you can get data in, not just from a NASA website, but you can also get it from a file if you have that. So I'm going to open this. And once again, RETScreen correctly interprets the top line as a header. And if I advance to the columns, because this is, the output saved from RETScreen, it correctly interprets pretty much all these columns here. And I don't really have to change anything. The only thing I do change is the relative humidity here. It's a fraction. But everything else is correctly interpreted, so I can import this weather data. And there I have, for each day from year 2000 to, I think, 2022, estimates of the air temperature, the relative humidity, the precipitation, the daily solar radiation on the horizontal, the atmospheric pressure, et cetera. This is all very well and good. It's got most of what we want. However, there's a problem. This is the daily solar radiation on the horizontal, and our modules aren't horizontal, right? They're tracking the sun. So ideally, we'd want to add a column here that had the daily solar radiation on a sun tracking surface. And actually, we can get that. Up here, we can go solar tilted, and we can pick the type of tracking, and we do have 2-axis tracking here. So I pick OK, and it adds a column over here at the end, which has the daily solar radiation on a tilted surface. So that's great. We now have a table that has both the daily solar radiation on a tilted surface and the average air temperature. So the two factors I want. The problem is this is on a daily basis, and I have over here in a separate table the electricity production on a billing period basis. So I'd want to get 2 more columns in here, which have the solar radiation on a 2-axis tracking surface and the air temperature for each billing period. And I can get that by going to merge here. So I want to put into this electricity production table the daily solar radiation on a tilted surface taken from the weather table. So I click OK, and here I have exactly what I just said I wanted to get. And I do that again, and I get the air temperature. And now I have what I wanted, right? A single table that has both the electricity production, the revenue, and the daily solar radiation, the air temperature. So then I can use this data to come up with a relationship that simply using this information estimates this. And I'm going to do that in the next tab. But before I do that, I just want to show you that you can generate an annual summary of your production here. And this might be useful if you wanted to see, rather than looking at these billing periods year by year, what was your system producing and what was the revenue associated with that. And you might be surprised to see that it's calculated the electricity export rate as being 80.2 cents per kilowatt hour. Seems really high, but that actually is the correct number. This was an old project done under Ontario's feed-in tariff program, which had 80.2 cents a kilowatt hour. So let's go now to the next tab where we will try and develop that equation that relates the kilowatt hours of production to the tilted irradiance and the average air temperature. And I'm going to start out by doing a baseline using only solar radiation. So I'm going to ignore temperature for now, for 2011 to 2018. So I'm using all the available data, and I'm going to predict the electricity production using the solar radiation. And when I click on that, RETScreen fits a line. See this line? It fits a line. So if you want to predict the electricity production in kilowatt hours per day based on the daily solar radiation, this line is the best you can do to fit through this cluster of data points. There's the equation for the line. There's the R squared value, the coefficient of determination. We can see that this electricity is expressed in kilowatt hours per day. Why is that important? Because by dividing by the number of days in the billing period, it's removed the variability due to the number of days in the billing period. So this is already solved for one problem we had with variability. Now, this is using all 7 years of data. It generates a line that does a pretty good job of approximating what we measured, right? The measurement is in green and the prediction based on this equation is in blue. So it's doing a pretty good job. But we might be able to do better by doing a regression analysis with multiple factors. So I'm going to do a baseline using solar rate and temperature for 2011 to 2020. And I'm going to use the solar radiation and the air temperature for this. And when I click on that, I get another baseline here. And I see the equation is slightly better here. The line, once again, does a reasonable job of matching what I measured. But what I think would be really interesting would be to look at the Q sum. And you'll see why in a second. So just to refresh your memory on what this Q sum is, it's going to take the difference for each billing period and do a running sum of that. So there's very little difference in these first 3 periods. So you'll see the running sum will stay near 0. But then we see that the actual electricity falls well below the prediction. So we're going to see negative numbers. And we're going to see those negative numbers accumulate to this point in time here. So we're going to see 3 data points where the line goes down. And then here, the prediction exceeds, or rather the actual electricity measurement exceeds the prediction. So we're going to see the slope reverse. So let's click Q sum here, cumulative sum. And that's precisely what we see here, right? Horizontal, no accumulating differences. And then we've got underperformance here, and then a period of actual performance exceeding predictions, and then some problems at the end. So each change in slope here tells us there's a change in the underlying performance of our system. We're fitting a single equation. The equation isn't changing. Obviously, the system is changing. Now, what I want to do is I want to use this to estimate the correct operations of the system. I'm running out of time here, but hopefully you can give me a few minutes here. I can see that the system's slope of this line is pretty stable for about a 3-year period, ending on Valentine's Day 2017. So it goes back to here to March 17th, 2014. This period, we got a pretty straight line. And furthermore, it's a line where the actual performance is exceeding the prediction. So things are going well for the system. So I'm going to assume that this represents stable, correct, no fault operation of my system. And I'm going to generate a new baseline just using that data. And this baseline is stable baseline for stable, no fault operation. And I'm going to use the same variables to predict this as we just used. The difference, of course, is that I am going to end this on Valentine's Day 2017. And I'm going to take about, say, 3 years of data here. And if I look at that in terms of months, I see that I've got a little bit too much. It's about, say, 34 months. Takes me from, March 18th, 2014 on to Valentine's Day 2017. So now I've got an R squared of 0.97 because there's very little variability in that slot in the slope of that line. So a single equation can fit the line very well. If we look at the line here, we see that the prediction matches the actual measurement very closely. So we can go and do a control chart now with this, where we compare the actual measurement minus what we predict with this baseline equation. And we can do that in absolute terms here. And we can see, generally speaking, they match each other very well, but there's a problem around here. And of course, this is the date where we observed there was a problem before. Quickly stands out that there's a period here in 2017 when there was a real problem. But after that period, it's not so easy to tell whether things were still functioning incorrectly or whether there continued to be faults. And to get that, we're going to use a Q-sum. So when we click on the Q-sum, we see flat line through to this red line, which represents Valentine's Day 2017. So the flat horizontal line means no accumulating difference between prediction and measurement. But boom, Valentine's Day 2017, something happened, and our predictions significantly exceeded what we measured. That is to say, we had underperformance. And things flattened out a bit here eventually, but there was a persistent problem. It's clear. That wasn't so obvious before, but now we can say there was a persistent problem that wasn't solved until July 17th, 2018. And due to all those problems, we can observe that if everything had functioned correctly, we would have had this straight, flat, horizontal line continuing on this way, but it didn't. We had a decline here. And the difference between that horizontal line and this line is the production that we essentially missed, which works out to 2,500 kilowatt hours of production. And we can also see that on a measurement and verification graph here. So the difference between these two lines indicates the shortfall in performance, and it summarizes what we just found there. So I've kind of run out of time to show you how you can forecast and do some other interesting summaries here. But you can see that we were able to detect the faults, both the extreme faults that were happening in a given time, and then persistent faults. The Q-sum and the control chart don't tell us what caused the fault, but they tell us when it happened, how severe it was, and those clues are really useful for figuring out what's going on in your system. So I've taken 3 more minutes than I expected to. Are there any questions?
That was awesome. Thank you so much, Michael. There are some questions here for you. The
Great.
first one being, For sizing your PV system in terms of kilowatts, how would you do it based on available roof area as the input rather than defining the kilowatt capacity as the initial input?
Yeah. So if you look at RETScreen's outputs there, it tells you the total solar collector area, which is based on the kilowatts of capacity and the efficiency. So you can pick the efficiency of your modules and then adjust the kilowatts of capacity until you get the roof area that you think you want to have. Now, the one caveat on that is it's telling you the solar collector area, not the roof area. So if your collectors are mounted flush on the roof with no space between them, if your panels are mounted on the roof with no space between them, then that's the same. The solar collector area, the solar panel area, and the roof area are the same. But if they're tilted up on a structure on a flat roof, for example, they're not going to be the same. And you're going to have to do a calculation outside of RETScreen to convert from roof area to solar collector area to come up with that.
Beautiful. Thank you so much, Michael. Got another one here. For performance analysis of wind farms, can we use the same approach shown today for a photovoltaic system?
Yes, but it is complicated a bit. Now, if you think back to the power curve for a wind turbine, it's highly nonlinear, right? It has zero at low wind speeds, and then it ramps up with something like the square or the cube of the wind speed. I mean, in theory, it's the cube, but in reality, it doesn't necessarily follow a cube. And then it flattens out as it approaches the nominal power of the wind turbine. So that's a highly specialized function. And if you're trying to fit a data points to that function, it's going to be challenging. The good thing is the energy curve, not the power curve, but the energy curve, which expresses the output of your wind farm as a function of the average wind speed. So if you're saying the, annual wind speed, average wind speed is X, it provides the energy that would be produced over the year. That tends to be a bit more linear. And even if it wasn't linear, you might be able to fit a nonlinear equation to it. But it's not as straightforward as with solar photovoltaic projects. It really works quite well with solar photovoltaic projects. It's a bit trickier with wind projects. So don't blindly apply the technique to wind farms. Give it a try, but be aware that you're doing something that's fundamentally more challenging because you're starting it with a nonlinear relationship between power and wind speed.
Gotcha. Awesome. Thank you. Got another one down here. It says, can RETScreen Expert also do pre-feasibility studies of small solar and wind systems, such as photovoltaic systems for single-family dwellings?
Yeah, absolutely. So I showed big projects here, 250 megawatt wind farm and 10 megawatt solar project. There's no reason you can't use these for small home systems. It's the exact same type of analysis.
Beautiful. And just so you know, here I'm sifting through all the thank yous and wonderful presentations. So
Great.
everyone loved your presentation.
Thanks.
Got another one here. It says, when does it make sense to use the virtual energy analyzer to start a feasibility study? And when does it make sense to start with a blank feasibility study?
Well, a lot of that's going to depend on you, right? Like I actually like starting with a blank analysis because then I know that every number in the analysis comes from me. I'm not relying on anyone else's assumptions. But for a lot of people, they're going to be happy to have default values that are going to be in the ballpark. And it's going to speed up their analysis. And it provides them with a starting point that they can then adjust to match their circumstances. The only concern I have there is make sure you do understand what the numbers are. Don't blindly accept every number in there. Ensure that whatever RETScreen proposes is valid for your particular situation. But if you appreciate speed over having complete control, then the virtual energy analyzer is an obvious choice. If like me, you're details oriented and you want to make sure that you understand every last detail of your analysis, then a blank analysis is not a bad way to go.
Beautiful. Got one last one here in case unless any other come through.
Yeah.
But it says there are sophisticated engineering design tools for utility scale solar and wind projects like the ones we looked at today. What role is there for RETScreen when such tools exist?
Yeah. So that is true, right? I mean, people don't build $400 million wind farms like we were looking at without using just RETScreen, right? They have lots of other tools. However, those other tools are unwieldy at times, right? It can be hard to get them to quickly reveal to you the impact of a change in a parameter. And the red screen analysis is nice because it encapsulates all the different facets of a project, particularly at the feasibility, pre-feasibility study level, and allows you to quickly assess what the impacts of changes in variables are going to be without having to deal with these big unwieldy pieces of software. So it's not replacing those other pieces of software. It's kind of encapsulating their output and providing a kind of a high level overview in those big projects that can be useful for understanding the project. So if I do know, of wind developers who definitely use all the tools that are available, but also keep a red screen analysis because, it's a lot easier to change a variable in red screen and see what the impact is, as opposed to, going through the heavy machinery of running computational fluid dynamics software packages to come up with the change in the output and then putting it into a big pro forma and things like that. Yeah.
That's awesome. Thank you so much for those wonderful answers, Michael. Unfortunately, we have reached our time for today. Just before I go into our closing remarks, I wanted to once again extend a thank you to Michael Ross for being here today and giving that
My
amazing
pleasure.
presentation and demonstration. Also wanted to extend a big thank you to our sponsor, RETScreen. Last but not least, I just want to thank you, the audience, for your questions and participation. Thank you, everybody, and have a great and safe day.